Okay, we're back with one more video about combinatorics, and this is going to be how combinatorics can be used in a couple of situations in probability trees. And these two actually are pretty important results for something we're going to be doing just a little bit down the road in a few sections later. So let's look at this example here to get us started. A 5 children example. Consider the situation where a couple is having 5 children, and we're going to keep track of their genders. So we want to draw out a probability tree. Can you draw it, or at least visualize it really quickly? Well, it looks something like this. Male, female, first child, and then from there, male or female, second child, and so forth, for a total of 1, 2, 3, 4, 5 children. Okay? All the probability of male or female we're going to assume is exactly the same, so each one of these is a half. They're all independent events, so in fact every edge is a half. All the probabilities of the past then are a half times a half times a half times a half times a half, or 1/2 to the 5th, or 1 over 32. So there are 32 different paths through here, all are equally likely. Okay, so there's our probability tree. I didn't write all in all the halves or all the 1 over 32s at the end, but you can put those in if you'd like. Okay, so now the next question is, let x represent the number of female children. That's a random variable. How many paths are there for each value of x? So for example, when x is 0, there's only one path. It's this very one at the top. When x is 5, there's only one here at the bottom. But there are lots of paths with just one female. There are lots of paths with just 2 females, lots of paths with 3, and quite a few with 4 females. So see if we can figure that out. And the trick and the hint is we want to try to use combinatorics to help us figure this out. Okay? We're trying to count the number of ways of distributing the correct number of the x females along the different paths. And once we have that figured out, can we go ahead and figure out the PDF table and graph? Okay, so if we're counting the number of females, x, we're counting the number of ways of selecting the x slots, first child, second child, third child, fourth child, or fifth child. The x slots that have females in them. At this point, we don't really care. Once the slots are picked, like the first child, third child, and fourth child, they're all the same if they've got all f's in them. So it turns out to be just 5 choose x. And so the PDF table and graph looks like this. So the number of paths that have 0 children, 0 female children out of the 5 total is 5 choose 0, or just 1. That was the path along the very top. Male, 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 male. Similarly, the one at the bottom is also 1. That's 5 choose 5, which is also 1. So each one of those has probability 1/32, or 0.3125. Now, what about how many ways can you have, how many different paths give you just one female child? Well, of the 5 slots, we're choosing one of them to be female, so that's 5 choose 1, which is 5. So there are 5 choices. Could be the first child, second, third, fourth, or fifth. So that's 5 choices there for the one female. And so then each one of those has probability 1/32. So multiply or add those 5 1/32 together. That's 5 times 1/32, or 5/32 in decimal form. That's exactly 0.15625. Similarly, choosing 5 choose 4 is also 5 down here at the bottom. Choosing the slots for the 4 female children down here is equivalent to choosing the 1 slot for the male child, and there's 5 slots for that altogether. So that's 5/32, or again 0.15625. For these 2 middle ones, 5 choose 2 and 5 choose 3 are the number of ways of doing it, and that's 10 either way. Of course, if you're counting number of ways of figuring out where the 2 females go, then you're also counting the number of ways of distributing the 3 males, and vice versa. So both of these turn out to be 10, and generally these combinations or binomial coefficients are symmetric here, the symmetry we saw in Pascal's triangle. And So that's 10. So this is 10 30-seconds, or 5/16 for both of these, or 0.3125. And of course, if you add these up, you do get 32 30-seconds, or 1, or the decimal versions add up to 1. If we take these numbers here and now do a bar graph for that, we get the graph of the probability density function. So this is the PDF table. Ignore the middle column. The X and the PDF of X is the PDF table, and then the graph is over here. So there's a good way of using our counting, our combination, to help us figure out some probabilities. And in fact, this is a situation we've looked at before. Let's take another kind of situation we've looked at before and see how we can use some of our counting arguments in this situation too. Suppose there's a collection of n equals 10 items, of which m equals 6 are good items, and so then n minus m, which is 4, are defective items. And we're going to choose 4 items from the group without replacing them. So at each stage, we're going to use S for successfully getting a good item and F for fail for selecting a defective item. So let X be the number of good items as is selected. So let's draw a probability tree and use and then eventually we're going to use combinatorics to help us get the PDF table and graph. So here's a tree actually worked out. 6/10 the first time. The next one is 5/9 here. This is something we'll call a hypergeometric distribution, which we're going to talk more about later. But you can see this kind of worked out. Now these are not reduced fractions at the end, but you can see what they turn out to be in this case. All of these, of course, will reduce quite a bit. Okay, but let's look at another way of figuring this out. And we can use some combinatorics. Okay, again, let's say there are n equals 10 good items, or 10 total items to choose from. Now we're going to choose from those 10, we're going to choose 4 items. So and we don't care about the order, so there are 10 choose 4 equals 210 ways of doing that. So that's the denominator. So all of these are going to have 10 choose 4, or 210 as the denominator for these probabilities. Now, if you think about it, there are 6 successfully good items to choose from, and we're going to choose X of those. So that's 6 choose X ways of selecting those successes. But then we have to select the failures as well. There are 4 failures to choose from, and we're going to choose 4 minus X of those for our failure, for the number of failures. So a number of different ways of choosing a failure of the 4 minus X failures. So the product of those two is going to be our numerator. 6 choose X times 4 choose 4 minus X. And of course, divide that by 210, that's going to be our PDF formula. So if we work these out, 6 choose 0, well, 6 choose 0 is 1, 4 choose 4 is 1. So this is just one way there of getting 0. That's 1 over 210. 6 choose 1 times 4 choose 3 is 24. So 24 over 210 is the probability of getting 1 success. 6 choose 2 times 4 choose 2 over 210 is 90 over 210. That's the probability of getting 2 successfully good items. 6 choose 3 times 4 choose 1 is choosing our 3 successful items and our 1 bad one for a total of 3 items. That's 80, and it's over 210 for our probability. So the probability of X equals 3 is 80 over 210. And then finally, for 4 items, it would be 6 choose 4 times 4 choose 0 is 210. Divided by 210 is 15 over 210. Now, if we reduce those fractions, they turn out to be 1 over 210, 4 over 35, 3/7, 8 over 21, and 1 over 14. And you can see those here in the graph of the PDF function over here. The 1 over 210 is so low it's hard to even see the bar there, but it's a non-zero, but not pretty close to 0, but not 0 bar there. And so this is an example. So these two examples turn out to be related to what's called a binomial distribution and a hypergeometric distribution, which we're going to study in quite a bit more detail in the next a couple of sections down the road. Good example, however, of using our combinations.